Con el segundo track, con la segunda presentación del track de la nube App Engine y más. Les pedimos a los que están hasta arriba particularmente si pueden acercarse al centro, porque para dejar espacio para más gente. Bueno, vamos a continuar con la plática de Ikai Lan, que probablemente tenga el título más largo de todo el evento. Diseñando para High Replication Datastore con Google App Engine, cómo tomar ventaja de la arquitectura distribuida de Google para construir aplicaciones confiables y robustas. Esta plática es de nivel avanzado y está enfocada a los usuarios de App Engine que deseen conocer más de las ventajas que esta plataforma representa y que pues, quieran aprender un poco más de cómo funcionan los sistemas distribuidos. Entonces, Ikai es ingeniero de programas para desarrolladores, está especializado en la parte de Google App Engine y antes de Google trabajó como ingeniero programador construyendo aplicaciones móviles y redes sociales para LinkedIn. Y bueno, vamos a darle la bienvenida.
Testing, is this thing on? Good morning, everybody. Buenos dias. This presentation will be in English. I'm very sorry. So my first question is, how many people here have developed using Google App Engine before? How many people here were here for the last presentation given by Chris Schock? So a couple of my slides in the beginning will look familiar because they're better versions of his slides. So just as a warning, is there anyone here that doesn't write code or doesn't program? Raise your hand so we can laugh at you. I just wanted to warn you, this talk can be very advanced, and this talk is going to be very, very technical. So if you don't understand tech topics, or if you don't know how to code, you will get bored very quickly. So first, let me introduce myself. My name is Ikai Lan, and you know, it is correct. I do work for Google, and I work for Developer Relations Group at Google. This is my contact information. They didn't go to my slides. I work for Developer Relations, and I'm based out of San Francisco, California. So I'm very happy to be here in Mexico. I have not had the chance to change money yet, so just so you know, I'm completely helpless in the city. So one thing that I thought was really funny was when I read this profile. My Spanish-speaking friends read this profile, and they came up to me, and they all started laughing because this profile was directly translated from Spanish. And it's obvious it was written by a human translator, possibly with the help of Google Translate. But when you read this profile, something's not right. I mean, let's look at this last sentence first. Let's look at this last sentence. This translates very, very poorly into Spanish, but it works well in English. If you think about what this is saying in English, it's saying, yes, my favorite sports teams, they all suck, right? But this is what happens when you have machines doing things. So we're still very far from machines being able to take over simple tasks that human beings like you and me can hopefully do, like translate from Spanish to English and English to Spanish. So today we have three main things we're going to try to do today. I'm going to give a quick introduction to what Google App Engine is. I mean, hopefully it seems like people have raised their hands, so you guys already build on App Engine, so that's not quite necessary. We're going to give a quick introduction to High Replication Datastore, and at the end I'm going to go really deep underneath the covers of High Replication Datastore to explain how this works. So again, if you're not already an App Engine developer, first of all, shame on you. You should be an App Engine developer. The code in these examples might not always make sense, but I've tried to make them as clear as possible and as generic as possible. The concepts in these slides, however, are always good to know. And you know, no matter what you do, be it on App Engine, off App Engine, using MySQL, MongoDB, Cassandra, just knowing these topics will make you much more fluent in being able to talk to other developers. So you've already seen this pyramid. At the bottom, we have what we call infrastructure as a service. And this is great. I mean, this was a huge innovation. I still think about the days when anytime I need to add a server, I would have to get in my car, drive to the local data center, go in, do the iScan. I don't think they had an iScan. I think they just had a key. So I'd open up with a key, go inside, open up a rack, install a new server, power it on, make sure everything was working. And then we got the cloud. You know, we had Amazon EC2, we have Rackspace, we have Join, and I have never, ever had to go into data center since these services have launched. So these services made me a very happy person. But what makes me really happy is a recent innovation that we like to call platform as a service, where instead of even having to worry about the operating system or any of these low-level details, We just write code and we push. Then we write code and we push, and we write code and we push. And Google App Engine falls into what we call platform as a service. And there's one other layer we like to talk about in this pyramid, which is software as a service, which are just things like Google Docs, Google Spreadsheets. So you build one of these on top of a lower layer. You know, you can't have docs and spreadsheets unless they're on some kind of a platform, and you can't have a platform unless there's some kind of an infrastructure. We like to call App Engine Cloud Development in Box, because as soon as you download the SDK, it covers everything you need to start deploying applications to Google servers. We support 3 language runtimes. The first one is Python. The second is Java. And when I say Java, I don't mean Java just the language. I mean the JVM. Anything that compiles with Java bytecode is something that will run on Google App Engine. So let's have a quick show of hands here for people that program in non-Java JVM languages. I see these are, all right, you guys are adventurous. So you guys are programming in Scala, Clojure, JRuby, Rhino, Groovy. These are all languages that will run on Google App Engine. And most recently, we launched Google Go, which, if not anything else, definitely has the best mascot out of all 3 languages. So Go is a language that I personally have taken on. I like Go quite a lot. Go is the Go team likes to call Go the next version of C, brought to you by the guys that didn't bring you C++. There are a lot of great things about the Go language, and it's a little bit out of scope of this talk for me to go into these things, but they're just great things like functional closures, interfaces, baked-in testing, fast builds. I highly encourage you check out golang.org when you get a chance. So let's talk about what App Engine does for you that's really unique. We have this concept known as dynamic scaling. So when you first launch your site, you know, let's say you're building a Facebook clone, because you know this is all rage now. In fact, even allegedly Google's doing it. You build out a low traffic site. We'll give you a number of instances that match the amount of traffic you have. But let's say your site starts to actually pick up steam and get popular. What do? We add more app servers. We just dynamically add more and more until we can serve what we need to serve for your application to work correctly. And this is probably the most updated slide, but we're up to 2 billion page views a day. Now, what type of infrastructure do you think it takes to build something that can support 2 billion page views a day? It takes something really unique and really special. But first, I'll talk about 2 of the customers that are really that I like to highlight. The first is a company called Web Filings. Public companies in the U.S. they need to file with the SEC every quarter, and Web Filings is extremely disruptive. Instead of doing your taxes, you know, on paper now, you can go in and do them online. And Web Filings is the same thing for companies. They started with 8 people, and now they're up to 200 people, and their entire infrastructure is built on App Engine. The second customer I like to talk about is the Royal Wedding. It's Kate and Will. This wasn't something I personally followed, but I later on found out that my mother stayed up all night watching this wedding. And when Kate and Will kissed, that's when we peaked at 32,000 requests a second. Now, think about that for a second. 32,000 requests a second is an enormous number. And one thing that I personally didn't understand was, why did this happen during the kiss? What was it about the kiss that made people go, I need to look at the website right now? I don't understand. So App Engine gives you a couple of core APIs, but today, as you know, we will be talking about one of the most important, if not the most important API in App Engine, and that's the App Engine's data store. In the earlier session, someone asked us if it was possible to export MySQL to App Engine's data store, and the answer was basically no. And the reason for that, it's not that the answer is no, it's just that MySQL and SQL hierarchies tend to be very, very complex. So App Engine's data store is schemaless and it's non-relational. So thinking about how your data maps to App Engine, to Bigtable, is a little bit more complex than just dumping and uploading. You really need to think about your access patterns. But the trade-offs for using a schemaless non-relational technology is that it's extremely scalable, but it also enables you to build very, very quickly. And we'll get into some examples of what that means. The most compelling feature of why you should use App Engine and App Engine's data store is High Replication Datastore. Let me tell you right now, building a multi-data center serving solution is very, very hard. All right? I've been on certain websites, and I'll just pick on Facebook, but you know, I pick on a lot of different sites. I post a status update, and I refresh my page, and it doesn't always show up. You know, why is this? Well, it's because they're serving out of multiple data centers. And it's very, very hard to do something where you have strongly consistent data that is written across multiple data centers. But this is what using App Engine Datastore allows you to do. You get consistent performance, you get high reliability, and most importantly, you get no data loss. Right now, a lot of the cross-data center solutions exist around, you have a master and a slave. The master replicates this slave, usually asynchronously. Now, what happens when a master data center loses power or blows up? You lose all the data that wasn't replicated. So App Engine's High Replication Datastore gets around this because every time you do a write, you are essentially doing a write to every single data center that App Engine is serving out of. So how do you use this as a client? You don't have to do very much. You just create a brand new application and remember the rules of strong consistency versus eventual consistency. So a fetch by key and an ancestor query, these exhibit strongly consistent behavior. Queries without an ancestor exhibit what's called eventually consistent behavior. And it's not always clear what this means, right? So strong consistency means that once you do something, once something is committed, every single view of that data will reflect the data that you just wrote. Whereas eventual consistency means that once you write some data, after some time, it may reflect. It'll probably reflect the data you just wrote. So I like to color this with an example. I don't know if I can hear you, but let's say I owe Arturo some money, right? Why would I owe him money? Yell out some reasons. What's that? Because he's awesome. Right? He's awesome, so I said, I'm going to pay you $20. So I take out a $20 bill, and I give it to him. Now, this is an instance of strong consistency, because as soon as I give him $20, his net worth goes up by $20, and my net worth goes down by $20. Right? Nothing in the world can change that. Everyone that looks at him knows that he is $20 richer, and everyone looks at me knows that I am, unfortunately, $20 poorer. Now, let's say I decide to write him a check. I go, you're so awesome, I am going to write you a check. So I write him a check for $20. I give him this check. Even though he has this check in his possession, he takes it to the bank, he deposits it. It doesn't show up in his bank account for 2, 3, 4 days, maybe a week. This is what we mean when we say eventual consistency. So that's what I'm talking about every time I say some of your writes will be strongly consistent and some of your writes will be eventually consistent. Here's an example of something that's very strongly consistent and always strongly consistent. And it's a get by key. In this code example, we instantiate the data store, we create a new entity, we save the entity, and we read the entity back. Now, in code, this executes maybe nanoseconds. It's nanoseconds between the save and the read. But since this is always strongly consistent, you will always get back the entity that you just wrote. This is also strongly consistent. Now, this code is a little bit more complex, so we'll step through it a little bit later on. We create an entity, it's a root entity, we give it a child, we do a query where we set an ancestor, and we say, give me back the data I wrote. And you will always, always get back the data that you just wrote. This is also strongly consistent. This is the same as giving someone $20 in cash. Now, here is something that is eventually consistent. This is equivalent to a credit card or a personal check. We create an entity. Notice that there is no root. There's no entity root. There's no ancestors being set. We do a query across all of our entities in our entire data store. We may or may not return the entity we just wrote because it's eventually consistent. If it was written fast enough, we'll get it back. If not, we don't. We have no guarantees. If we sleep for 300 milliseconds, chances are pretty good we'll get it back. If we sleep for 5 minutes, chances are near 100% we'll get it back. But again, it's all statistics, right? It approaches 100%. It's very hard to guarantee that something will always be 100%. Why is this? Well, the reason is that we do the transactions on the reads. We don't do the transactions on the writes. On a read, we try to determine whether or not we have the latest data. And we can only do this if we have what's called an entity group root. If we're not up to date, we catch up our local data store to the newest data, and then we return it. So to understand how this works, we need to have some understanding of Google's implementation of Paxos, which needs some understanding of how transactions work, which necessitates some understanding of how entity groups work in Google App Engine. So it's time for us to go really deep under the hood. Now, a lot of people in this audience have already done App Engine development, so you're familiar with the concept of entity groups. For those of you that are not,
you cannot perform transactions outside of an entity group. In this case, an entity group is a hierarchical ordering of entities. In this case, we have user, a user's many blogs, blogs of many entries. Now, if we want to transact on all three of these entries, we can do that. We can say either they all get updated or none of them get updated. But if we had two different users with two different blogs, we would not be able to transactionally do this update. And the reason is because we do locking on the entity group root. So this is the code we were looking at earlier. We're going to walk through it. First off, we establish an entity group root. This is what all the transactional locking happens on. And you show that we're creating an entity in a data store. So we add a child to this entity. Now notice that the second parameter to this entity constructor is the key of the root. That's because once you set a key, you cannot change it. Once an entity is in an entity group, you cannot move the entity outside that entity group. So what this looks like is you have entities that look like this. You have a root element, and you have a child that belongs to that root. So transactions lock on the root element. So let's talk about how transactional reads work. We've got the data store, and we have some data. And the version of this data is version, say, version 11. So we create a new client, and this client begins to do a data read. Now, we've got a different client, and this client wants to commit some data to data store. Now, this is version 12 of the data. Now, this data is still being committed. But because reads are transactional, we realize that version 12 is not fully written yet. It's not fully been committed yet. So the data store will always return version 11 of the data, because version 12 of the data has not yet finished committing. App Engine uses a system called optimistic locking, and we're going to show you what this means in the next slide. Now, what it means to be optimistic is there's a saying where you look at a glass, is the glass half empty or is the glass half full? And someone who's a pessimist will say, the glass is half empty, it's already half gone. And this is the type of person that will often say, oh, what's the point of going outside? It's going to rain anyway, right? Now, an optimistic person sees this glass as half full and is happy that, hey, I still have half a glass of water to drink. Now, optimistic locking in computer science and programming, what this means is that you assume most of the time when you read some data, no one else is ever going to change this data. And if your application is read heavy, this is almost always true. When you're reading some data, someone else will very rarely commit some new data. So let's show optimistic locking in action. Again, we have the data store, and again, we have some data, and it's at version 11. So the client begins a data read. Now we have a second client, and now the client has in its local memory version 11 of the data. So we have a second app server, and the second app server commits back some data to version 12. This is an updated version of the data. Version 11, so now in the data store, it has been committed. The version that's in there is version 12. The first client begins to modify this data and starts to write it back to the data store. What happens? This throws an exception. This is an optimistically locked transaction. Why? Because most of the time, when an app server reads data and writes it back, you don't have some other guy here writing in data. So most of the time, you're not doing any additional work. You only do additional work when you write back the data. Someone throws an exception. You say, OK, I need to take this data back, do some work with it, and read it back. That's the only time you do more work. That's why we call it optimistic. You're optimistic. You don't have to do more work. You contrast this with pessimistic locking. The difference between optimistic and pessimistic is that if version 12, if the second app server tries to read data to modify and check it back, no other clients can read the data, because the data store will say, no, someone's doing something with that. So just hang on until you're done, and then you can read the data. So optimistic locking, I have to go through the animations again, is really good in places where things are very, very read heavy. But if it's very expensive to redo a transaction and to recalculate new values, you probably want something like pessimistic locking. Now, App Engine only supports optimistic locking out of the box. Okay. So now we're going to talk about the distributed write portion, because the examples I just covered only talk about a local data store and a local write. When we talk about high replication, I say that things are committed to multiple data stores. So what really happens? Well, you've got a server. You've got an app server. The app server writes some data to the data store. What the app server is really doing is it sends an RPC to multiple data stores, and a majority of data stores have to respond back and say, I receive your write. And once these data stores say, I receive your write, the app server, your method stops blocking, and the app server knows, okay, my data has been committed. But what's really happening is that the data stores are taking these writes and adding them to the journal of writes. So if you've ever used something like a binary log in MySQL, a journal is a list of things that you need to apply. They don't happen right away. It's just a promise that at some point in the future, you will write this data to the data store. And the reason is because append-only file systems are very, very fast. Think about it. Think about append-only data structures. Think about what a linked list looks like. If you have a pointer to the last node in a linked list, it's very, very fast to append something to it. But if you ever want to modify things in place, out of order, and not at the tail of a data structure, it starts to get much more expensive. Instead of being an O of 1 operation, you have an operation that's O of n, or O of log n, or O of n log n, depending on what your data structure looks like. So it's the same thing that we do here. When we write to a journal, we append to the end of the journal. And when we have a different process that takes these journal entries and goes ahead and either modifies the data in a data store or creates new data. So I mentioned earlier that reads are transactional. What does this mean? What this means is that when an app server tries to read data from a local data store, the data store asks itself, is this the newest version of the data? And the data store knows this because the data store has a cache of what the most recently written data is. But it also has a journal. So it'll look at itself and it'll say, okay, is this the latest version of data? Yes, yes it is. So the data store just returns the data right away. And 99.99 whatever percentage of your data store reads will operate this way. But let's say there's a lag. Right? Let's say we try to read from a local data store, and it turns out that it's actually not up to date. Well, what happens? Well, the app server goes to a local data store and says, do you have the latest data? Now, as you can see from this journal, not all of the writes for item 1 have applied yet. We still have a version 26 that has not yet finished applying. So the data store says, oh no, I'm not up to date. I'm going to quickly try to catch up this data as quickly as possible before returning it to you. But there's one other optimization that High Replication Datastore puts into place, which is that when a local data store needs to catch up, the local data store also dispatches RPCs to every remote data store and says, it's a race. Whoever can return this data the fastest, that's what the client will use. And you know that it's always the freshest version of the data because every instance of the data store is going over the journal, looking at itself saying, do I catch up or do I return what I have? And if they're already up to date, they return what they have. And if not, they play catch up. So you're always guaranteed that when you do this transactionally, that you get the newest version of some data. So in this example, the reason you're able to do this is because, again, you're locking on a root entity. In a global query, there's no root entity to lock on. There's just many root entities. And this is an algorithm that simply wouldn't scale. In an ancestor query, you lock on the root of that entity group tree. In a get by key, you lock on that entity itself. So this is a grossly oversimplified example of Paxos and consensus in a distributed environment. But if you're interested in more details, this is all based on a publicly available white paper about a data store layer that we've built on top of Bigtable called Megastore. So I will post these online. Either add me on Twitter and Google+, because I will post these once I get a usable internet connection again. So I'm going to give you some contradictory advice when you're using entity groups in App Engine. Entity groups have to be as big as possible to cover as much data as you need, because when you want transactions, you usually want transactions across multiple data entities. It doesn't really bother that much to only have transactions on a single entity. But on the other hand, when your entity groups are too large, we ask people to engineer their entity groups such that they only anticipate one write a second. So this seems a little bit slow until you realize that you can have almost an unlimited, pretty much an unlimited amount of entity groups. So your entity groups need to be both as big as possible, but as small as possible. And that's why I like to say it's contradictory advice. There's no one single formula for whether something should be an entity group or not. One thing we usually recommend to people is that you put a user in an entity group, because it's generally rare that for one user, you will be doing more than one write a second. And usually you don't need transactions across multiple users. But then again, I've been proven wrong, and there are lots of cases where that's not true. So I talk really quickly because I really only have a few points to make. And I just wanted to summarize what I talked about today, which are that, first off, remember the rules of strong consistency versus eventual consistency when you're using App Engine's data store, which is a great feature. It's a great tool because it's extremely reliable, it's extremely scalable, and it also gives you strong data consistency if you know the rules, if you know how to play the game. Group your data into entity groups and use ancestor queries anywhere that's possible. Use get by keys when it's possible. Try to avoid global queries unless you don't care about consistency guarantees. So I wanted to open this up to questions. Questions about the data store, questions about App Engine. If there's any other slide that you want me to go back, I have a tendency to talk quickly. I don't mind going over a slide that I already went over. I will post these online. Did I just blow everybody's mind? That's okay, I was like this too. I said, the what does the what?
Hi, my name is Gerardo. I apologize for my English. It's not as good as you. So my first question is, I don't know to understand. Google App Engine use optimistic locking,
Yes.
but that means that it doesn't use transactions in the...
Optimistic locking is a way of doing transactions. So if you, let me go back here to this slide. We'll show everything out. So optimistic locking just means that pretend that the data has some version. When you write the data back, you want to increment the version. So if you increment the version and it's equal to or less than the version that's already in the data store, that's going to throw an exception. That's what optimistic locking means. So that is transactional because it means that you can't read data and check it back if the data is stale, if some other client has already committed that data.
So in the end, you have one column that has a date stamp, for example, a time stamp?
Basically, yes, yes. Bigtable rows have, Bigtable rows store individual, not really timestamps because sometimes, you know, in the distributed systems, the timestamp doesn't do anything. You care more about order, so it's a version number is more important than the actual timestamp. You just care about what order the data came in. So Bigtable keeps the last few versions of some data, and this is used for rolling back transactions when things don't work out. Okay. Yeah.
Thank you very much.
No problem.
Hi, this is Sparta. Is Google Plus using this kind of data store?
Google Plus is built on top of Bigtable, and the white paper that's in this link points to Megastore. I don't know if Google Plus uses Megastore, but most systems, when you want to scale them out, you want to build them using eventual consistency. Like one thing you'll notice about Google Plus, you might post something and you IM your friend, you say, hey, look at my newest Google Plus post, and they don't see it right away. So that's an eventually consistent system because those are much cheaper and easier to scale out. So Google Plus does use Bigtable. I don't know for a fact if they use Megastore. Google Plus does not use App Engine, but many of the components they use are also used by App Engine.
So Bigtable is all stuff?
What's that?
Bigtable is an all stuff? You are using Megastore in the news projects?
Bigtable is basically used everywhere at Google. There might be one place where Bigtable is not being used, and I think it's one of the ads teams. Uses a combination of Bigtable and I think some implementation of SQL. Yeah.
Thank you.
No problem.
Hello.
Hello, Sergio.
Hello.
I know names.
You talked about, or the previous guy, Chris, talked about a relational database that was being applied to App Engine. Can you talk a little bit about that?
Of course. So the relational database he's talking about is something that's currently in a closed alpha. I think my understanding is they more or less decided they needed to rewrite the whole thing. How many of us developers have at one point said, oh, forget it, I'm just going to rewrite this whole thing from scratch? It's both gratifying, but it's also infuriating when you have to solve the same problems again. But the thing that they're talking about is called hosted SQL, and it's really meant for small to medium-sized data sets that need highly relational, a highly relational data set. I've heard of one instance where there's one of our testers that's using it. Well, what's happening is he's throwing too much traffic at it, and he's throwing just tons and tons of data at it. And we realized that he needed to shard his hosted SQL instance. And at that point, I just said, why didn't you just start from Bigtable in the beginning? But it's sometimes hard to win these battles. We haven't announced anything about when we'll release that yet. But again, we're targeting that for small to medium-sized data sets and small to medium-sized loads. Okay.
Okay. You said there's only optimistic locking out of the box. Is there some way to get a standard pessimistic locking?
There are definitely ways to do pessimistic locking, but you more or less have to build them yourself. I mean, the idea is that pessimistic locking is, has been the bane of my existence for there was a period in my life where pessimistic locks were causing me so many problems, and most of those problems are related to scalability. There's no way natively to do pessimistic locking, but I can envision some way in which you're using some combination of either memcache or using the optimistic locking mechanism to guarantee pessimistic locking. I think there's some way, I'm pretty sure there's some way to build that. Yeah.
Hi, this is Julio.
Hi.
When do you recommend to use Bigtable instead of Facebook's Cassandra or MongoDB?
Well, you can't really use Bigtable because only we have it. But to answer that question, one of the things I like to do in, I'm like a super nerd, right? So I love giving talks about MongoDB and Python and Ruby and all of these things that have nothing to do with my job at Google. MongoDB is just, to me, is just a world of fun. I mean, I love MongoDB. Cassandra I have a little bit less experience with, but out of all the NoSQL kind of data stores, between I think Riak, which is run by Basho, Cassandra, and MongoDB, these are really the only three open source databases that have production support. Like you can buy support and you can buy consulting. Some of these other ones like Tokyo Cabinet, Project Voldemort, these don't really give you the ability, like you can't pay someone to come and help you. So out of those three, it just depends which one you like. I think it's easiest to get started on MongoDB. I mean, to get started on MongoDB, you download binary and you run the binary. Right? To get started on Cassandra, you download Cassandra, you read through a bunch of docs, you try to set up your columns, you do it wrong the first time, you read the docs again, you do it wrong again. So I think that ease of adoption is also a nice thing. Riak, I don't have enough experience with, so I couldn't tell you about that. I personally like MongoDB.
Thank you.
I don't know what else to say. I like MySQL and Postgres too. Great databases. Postgres is also really, really fast. MongoDB, the default writes are asynchronous, so you can write some data, and MongoDB never tells you if it's wrote the data or not. So if you turn on MongoDB's, like, I'm going to tell you that I wrote the data for sure, it's only a little bit faster than Postgres. Not enough to make a difference, I think. So. Okay, well, I'll be around all day. I'm wearing this shirt unless they force me to put on the white shirt. So you can find me, and I'm giving a talk in the afternoon. The talk I'm giving is about REST, JSON, and OAuth. It is a very beginner-level talk compared to what went down today. So it's only if you're completely unfamiliar with those concepts. But the OAuth stuff is kind of interesting. So, okay. Thank you very much.